Hello, my name is Bob Golding, and I'm a senior escalation engineer at the Microsoft Charlotte facility. Again, I'm making a video, another video. This time will be on memory management, and it's called Map File Madness. I'm going to explain a little bit about how map files work and about PTEs and shared memory. This is a presentation I gave a little while back. Some things in memory management have changed slightly since the conception when I first created this presentation. But I just want to get out the basics on how this works. I'll touch upon changes that a little bit during the presentation, but I just want to give everybody the basics on how this mechanism works. And part of the presentation I'll be going through this is part one. Part two, I'll go through a debugger session and present some of these structures, and then we'll go over the structures that I presented a little bit via slides. I just wanted to say that anything that I present that's not in MSDN is subject to change without notice. So let us begin. Okay, the first thing I want to talk about is a review about PTEs. PTEs are for logical addresses. The hardware works on physical addresses, and that's how all the caches load data. But we have memory protection. So you could take a logical address that maps to a physical page, and you could set the access on the page for like read only, and there's some other bits as well that can be set in there, execute, protect. But how we get to that from the logical address is in this diagram above. More can be found in the Intel manual. And if you can see you get a CR3 register in the system points to the base of all the translations, and then the logical address is sent through the hardware. It's broken up into pieces, and the very last piece at the end has the page table entry that has the physical page to where to translate for the final translation, and then the last 12 bits are the offset into the page, the byte offset. More can be found a description in the Intel manual. And the PTE contains access rights, a logical to physical translation. There's a valid bit. If it's not set, it'll cause the operating system to enter the page fault handler. Information as far as the logical to physical translations can be cached. There is a transaction look-aside buffer, it's called. It's an address translation cache. From a long time ago at Data General, if you get a cache miss, we used to call a LAT, which is a long address translation trap. And if it's a cache miss, it'll force the microcode to go do a PTE walk and load the translation into the transaction look-aside buffer. The valid bit, again, if it's not set, you'll transfer control to the page fault handler in the operating system. Now, since the TLB is a per processor entity, if a change is made in a PTE, all the other processors need to be notified. So if you have a system address that's removed, okay, say we free a page of memory, or we add a page of memory to the logical address space map, we have to well, remove is probably a better example. If we remove it, we have to be sure that there are no translations in any other caches. Because if the logical address gets repurposed, we need to be sure that the correct translation is loaded in the cache. If there's a stale entry, the hardware doesn't know, and it's just going to use that logical address to access a stale address translation cache entry, and you won't get the correct logical to physical translation. Now, if the valid bit is not set, since the hardware only cares, will load it into the cache and use it if the valid bit is set. If it's not, software can use the remaining bits for how it sees fit, and that's how the shared page mechanism works. Plus, there are for how the operating system determines when it takes a page fault what to do. For example, the valid bit won't be set, and if the translation resides in a page file, there'll be page file information in the PTE. So if a page fault occurs, it could just bring it in from the page file. The page file offset, page file number, and I believe the access bits are all stored to PTE, and the valid bit is not set. So if a page fault occurs, the software can turn around quickly, read in the information from the page file. This is a picture of the transaction look-aside buffer. So you can see that we do when a logical address read is initiated, the cache is checked, and you see that the example is virtual page number 17. Virtual page number 17 maps to that location in the TLB, and it has the physical address translation. The translation is immediate, and we don't have to do a PTE walk to get to the physical translation since it's in cached. This is a picture of a PTE. The bit 63 is the no execute bit. There's a working set index, offset, that's for quick lookup. All processes or pages that are valid have a part of a working set list, so so memory management can manage it and maybe remove a page if it's aged, depending on the memory demand. And that's so it can quickly look up if it finds a page, finds a PTE, you could go back and find a working set entry for it. There are some other bits of interest. There's the valid bit, which is bit 0. Write says the page is write enabled. If the page is not write enabled and you try to write to it, you'll get a access violation. There's a dirty and an accessed. The dirty bit means the page was written to. If the page is written to, the hardware will write the dirty bit into the PTE so the operating system can know that the page has been modified. The access bit is if it's read or written, the access bit will be set. And this is sometimes it's used as a hint to whether or not it should be invalidated if it's necessary to invalidate the entry in the address translation cache in all the CPUs. So theoretically, if the page hasn't been accessed, that means the hardware most likely has not loaded it into the address translation cache. So that's kind of, the operating system can use that as a hint to whether or not it does have to invalidate the page in all processors. Okay, this is this is a PTE from the debugger command bang PTE, and we have the bits in this particular example. It has the physical page. Physical page number depends on the memory size, physical memory size, how many bits it can take up. And in this example, 867 is the protection, which is the last 12 bits, which is, the translation is the page offset, so it's not necessary because we're working with 1024 byte pages most of the time for user mappings. 37 Charlie 5 is the page. physical page. In this example, it's dirty, it's been accessed, user mode page, um, and it's writable. So that is the that's just an example of bank PTE. And for every physical page in the machine, there's a structure called a PFN. PFNs are pretty compact and small. Some of the offsets are a multi-use depending on the status of the page, because for every physical page in the machine, there could be a PFN that describes the page. Okay, there's a working set index offset, the PTE address that belongs to that physical page. There's a share count and a reference count. Okay, the share count is how many places that physical page is mapped. For a shared file, if there are 5 processes that are using that physical page, the share count is 5, meaning there are 5 mappings. The reference count is usually 1. Okay, when the share count goes to 0, the reference count is decremented, and the share count reference count go to 0, the page can go on either the standby or the modified list, depending if if it's modified or not. The page is still in use. No, of course, it's different if the address space is being torn down. Okay, so and the reference count is incremented. Like if you want to lock a page, the reference count is incremented. So it will not go to 0 till all I/O is complete to stop it from being repurposed while there's I/O in progress, so the page doesn't get destroyed if it's repurposed. And then there's the original PTE contents. We'll talk about that more later. And then there's the PFN number, which is the physical page number. And this is an example of a bank PFN command that's used in the debugger. And in this example, share count is Charlie, saying there are Charlie mappings to that page. The PTE address for that particular page is a page priority. The page is active, meaning it's not on standby or modified list. It's active. It's actively in use. There's the restore PTE. Again, we'll talk more about that later. And in this example, the reference count is 1. Okay, and you can see the F link, B link, share count. See, they're all they're multi-use. The F link is actually, I think it's either forward link, and the backward link is the share count, and the forward link is the offset, the working set index offset for that page for the process it's mapped to. The containing page is the pointer to the previous page that contains it, the PDE. Okay, so that basically how PFNs are all about. Now this is the basic basic life of a page, I guess, if you will. It depends on when it's removed from a process because of aging, depending on the memory demand. It's going to go out of the working set into the modified list. Modified page writer will write the page, and it could go on standby. And from standby, depending on the memory demand, it could be repurposed. The PTE will reflect where the page, and it'll be called transition. If a fault occurs in the process, it'll be taken off the standby to modified list and put back in the process's working set again. And if it has to be written, it's either written to the backing store if it's a shared page, or it could be written to the page file if it's a private page. If it's written to the page file, the PTE will have information of where in the page file is protection, okay, without the valid bit set. And shared pages we'll talk more about in a bit. In processes, there's something called a VAD, which is a virtual address descriptor. And virtual address descriptors for shared pages have what's called a control area. Control area describes the file that it's backing store. You have a segment and subsections. Segment describes the mapping for the entire information about all the subsections, if you will. Each subsection has a different protection. In say for an executable, the subsections divided up based on the file header, and we'll look at that later in the presentation. But on a data section, all the subsections are the same size, and subsections are a grouping of PTEs. Okay, and in a subsection, I don't know offhand the subsection size for a user data file, but for we'll see more about this later in the presentation. But subsections for backing store with data files are a fixed length. I think it might be 2,000. But for executables, there's a maximum size. That might be 2,000, but it's broken up based on the header. And the header could be displayed through with the debugger command bang-dh. Okay, the user PTE commands, the user PTE array, I'm sorry, will since the PTE bits, if the valid bit is not set, can be used for software, the PTE bits in the user PTE array can be used to point to the subsection of the file on a page fault. Okay, and that's basically how we do that for shared files. So we'll look at that. We'll look at that later, but that's how it works for each. So for each DLL, you take a page fault, and it's been removed. What could be if the PTE is 0, what we do is that we put what's called a VAD lookup PTE in there, and we validate the address. The address is valid. A VAD PTE will be put in there, and that tells the memory subsystem that this is a valid PTE, and it could be look up in the VAD, and the VAD will have information about the subsection and or the control area that for the backing store. In this case, we have 2 DLLs, and we'll see that later what this means. So the user PTE array will have pointers to the subsection. And as I mentioned before, the PTE array can point to the subsection PTEs, and so you have PTE array B. So the way it works is that the PTE actually, when we take a page fault, to get the PTE, we go to a PTE that's in what's called a subsection. In the subsection is the actual PTE, and the PTE gets stored in the PTE array in the process address space. The subsection, for every user that brings in the subsection PTE and maps in the PTE array, we bump the share count. Okay, and for every process, it's going to have a VAD that points to the subsection control area. So here in this example, we see that PTE array A points to the subsection PTEs for an event of a page fault. We can go get the PTE back, okay, because if the page is removed, we put the subsection address in the PTE. This will make more sense later when we get into the debugger section. But the actual PTEs are in what's called the subsection. So if you do take a page fault, the PTE gets taken out of the subsection and put in the PTE array. That's how sharing is accomplished. That's what this diagram tries to explain. Okay, next we have the debugger demo. That'll be the next presentation. I think we go through the debugger to be able to see some of these things. It'll make more sense, and then we'll go in the next section. We'll go over what we saw in the debugger. I just what we did is this first presentation, just a high level view, and as we get into the details, I think things will make more sense. So stay tuned for the next presentation, and we'll get into the debugger, and we'll talk about and actually see the VADs, the segments, sections, control areas. We'll use bang DH, and we'll see we can see how the header of the file is used to create the subsections. So stay tuned for the next demo.